this presentation, I'll be discussing Lab 3. Introduction. The purpose of this lab is to use GlowScript code to examine the physical properties of a star orbiting a black hole of unknown mass. First, the mass of the black hole is calculated, and then in the second part, when a planet and ship were added to the simulation, the initial velocity a ship would need to not crash into either the star or the black hole from the planet was found. Our results were, the average mass of the black hole was found to be 2.13 e34 kilograms, and the initial velocity the ship needed not to crash was found to be negative 10 e to the 7, 5 e to the 6 meters per second. Here are the physical principles we used. In part 1, F net of the black hole on the star is the gravitation force, which is equal to gmm over r squared times r hat. Another F net was equal to the change in momentum over the change in time, and another F net formula used was F parallel plus F perpendicular. F net parallel is equal to the change in momentum over change in time, and F net perpendicular is equal to mv squared over r. In part 2, we use the gravitational force formula above, and we also use position and velocity update formulas. Why do we use these physical principles? The physical principles defined on the previous slide were used for this lab because this lab focuses on forces of gravity, which in these cases have parallel and perpendicular components. The equations under part 1 on the previous slide were needed to calculate the net force, which was needed to solve for the mass of the black hole. For part 2, the same gravitational force equation was used along with the position and velocity update formulas, which were needed to determine the path of the ship over time and to see if it crashed or not. The initial conditions for part 1, the mass of the star was 2 e to the 30 kilograms, the position of the black hole was at the origin, initial time was t equals 0, and delta t was 86,400 seconds, which is equal to 1 day. The initial momentum formula we used was the mass of the star times the initial velocity, and in this case, the system was the star, and the surroundings were the black hole in space. This code worked by finding the initial and final momentum of the star, and then finding the change in velocity and in momentum over this interval. This information was used to find F net. The parallel force was then calculated using the F net parallel formula, and the perpendicular force was then calculated by subtracting F net parallel from F net total. The mass of the black hole was found by rearranging the gravitational force formula. This code output values for the mass of the black hole over time, F net total, F net parallel, and F net perpendicular, as well as the model depicting the star's orbit. And here is that output shown in a video. The average mass of the black hole is 2.13 e to the 34, and the F nets are listed below as well. Potential errors. The mass of the black hole changed throughout the model, which obviously isn't correct, and this error is probably due to the very large delta t. A smaller time step would lead to more accurate results. For part 2, here are the initial conditions. We used the black hole mass as calculated from the previous code. The planet mass was 9 e to the 28 kilograms, ship mass 7 e to the 10 kilograms, delta t in this case was 1 second, and the initial velocity of the ship was changed to see at which velocity it would not crash. The system in this case was the ship, and the surroundings were the planet, black hole, and space, and this code also calculated the trajectory of the planet, and in this case, the system is the planet, and the surroundings are the black hole, the ship, and space. This code worked by using the position and mass of the black hole, the position and mass of the star, and the position and mass of the ship to first calculate the net force on the planet by calculating the net force on the planet by the black hole and the net force on the planet by the ship and adding them together. Then, calculating the net force on the ship by calculating the net force on the ship by the planet and the net force on the ship by the black hole and adding them together. Finally, the position and velocity update formulas were applied to the position and velocity of both the planet and the ship over time increments of delta t equals 1. Here are the outputs of this code. The previous information calculated by the code was used to determine if the ship crashed into the planet, was sucked into the black hole, or avoided them both, and in this case, they avoided them both. Potential errors. The mass of the black hole we previously calculated was not 100% accurate, and it was also rounded. Rounding during each iteration of the code could have big effects. What does it mean? Net force and its parallel and perpendicular components as it relates to the rate of change of the momentum and its parallel and perpendicular components. These two things are equivalent mathematically. F net equals F net parallel plus F net perpendicular, and that is also equal to the change in momentum over the change in time. The only difference is that the change in momentum over time can be observed and measured in this way, while the net force cannot be observed. This means that finding the rate of change of the momentum is a good way to solve for the net force. What if? What initial velocity would the ship need to orbit the black hole? I found this velocity to be negative 1.5 e to the 6 and 1.5 e to the 7 meters per second. And here is a picture of the beginning of this orbit. Thank you.